This video shows you and tells you about what happens when our reaction happens, when you follow the concentration or the production of products or the disappearance of reactants. In other words, what we call the reaction rates. So every chemical reaction has its own velocity, so you can measure it by, as I said in the beginning, measuring the consumption, the disappearance of a reagent, how quickly it disappears, or how quickly a product is formed. For example, if you put a bit of chalk, which is calcium carbonate, in some acid, the chalk dissolves visibly, as you actually can see the chalk disappearing and a lot of bubble forming. The reaction you saw in the former slide is due to the fact that the calcium carbonate, which the chalk is made of, reacts, for example, with hydrochloric acid in aqueous solution and becomes gaseous carbon dioxide, dissolved or aqueous calcium chloride, and water. Now, the visible bubbles is the gaseous carbon dioxide, which is formed by this reaction. The chalk disappears because the insoluble heavy soluble salt, calcium carbonate, is made to a soluble salt called calcium chloride. That's why the solution just becomes transparent. If you follow change of concentration or masses or volumes of reactants and products against time, it can look like in the next slides. In this slide you can see how a graph could look like in three different cases where we monitor the reaction we have been speaking until now, the chalk in acid. In the graph A, you're following the quantity of carbon dioxide produced time after time. So as you see, the production of carbon dioxide grows quickly, rapidly, until it gradually flattens out, and at a certain point no more carbon dioxide is produced because the acid has dissolved all the calcium carbonate. In graph B, we look at the mass of the flask plus the content. So really what you measure, it is the loss of mass or reactant, because obviously the volume of the solution and the mass of the flask doesn't change. What changes is the quantity of solid calcium carbonate, which is back in the solution. And as you see, it starts very rapidly by losing mass, and it gradually loses mass more slowly, and it comes at a point where all the chalk has been dissolved and the reaction has gone to completion at this point. So no more loss of mass is detectable. In the third example, C, you could look at the concentration of hydrochloric acid, and well, the best way of doing that could be actually to put a pH meter. So really you could actually have the pH values here, which will let you determine the concentration of hydrochloric acid. But anyways, let's see, this is the concentration of hydrochloric acid in mole per cubic decimeter or mole per liter. As we've seen before, we start from a certain quantity. The concentration at the very start of the reaction falls pretty much quickly. Then the fall of concentration of hydrochloric acid, which is a reactant, flattens out, and at a certain point, now it is not shown in the graph, you will see that the concentration of hydrochloric acid doesn't fall further, but remains constant. That means all of the chalk has been dissolved. If you look at both graph A, B, and C, there is something common. The dependent variable, well, here is the volume of CO2, here is the mass, here is the concentration, doesn't change linearly. So in this case, it doesn't change like this, gradually, linearly, proportionally. In this case, it doesn't fall linearly like this, and in this case, it doesn't fall either linearly, proportionally. That gives us a problem, which the next. In the case A, we have got, as we saw before, the monitoring of the production of carbon dioxide against time. Now, as we saw, the production of CO2 increases steeply and heavily and quickly at the start, then it flattens out, and then it reaches a point where no more CO2 is produced. Now, if we look at how we normally define something like velocity in physics, then it is a mathematical function which is linear, because the velocity, for example, velocity of movement is v is equal delta s, the space covered by the moving object, divided delta t, the time it took to cover the distance, delta s. But actually, if you look at this, it is a linear mathematical function. If we compare with our reaction, well, this is a curve. This is no linear mathematical function. So we need to find a way to measure the reaction rate, meaning the reaction velocity, avoiding this problem, which is the fact that the reaction velocity cannot be represented with a linear function. Now, in this case, we have got, as we saw, the volume of CO2 in the dissolution of calcium carbonate in hydrochloric acid, and we've got a curve and not a linear function. So the way of solving this problem could be to look at what we call the average rate. The average rate could be calculated by measuring a change of concentration in a short period of time. And in the particular case where we are looking at the CO2, it could be the change of volume, not throughout the whole reaction, but just throughout a period of time, like this, from, for example, 10 to 30 seconds. So what we are actually doing here, when we calculate reaction rate like this, we are just narrowing the time in which we calculate the difference of concentration. And that's a mathematical operation which is represented by this formula. That means we narrow the range of time in which we calculate the change of concentration. And mathematically speaking, that means if we have a function, a curve, which defines the change of volume in this reaction, what we are doing with this operation where we narrow the time in which we calculate the average rate, we are finding a function which is the tangent to the curve at a given moment. The tangent is the only linear expression, linear function, who actually shares one point, a single point, this one, with the curve. And actually, when we calculate the average rate in this way, well, we would have an expression which is like this. Change of volume divided short change of time, and the steepness of this line here will be the reaction rate. Let's call it R. So that's how you basically solve this problem without doing all too much. Now, when you have a graph like the one you saw before, you could actually, of course, determine the average rate, but the best way of determining the rate, it is to determine when the rate is highest, and that's in the beginning of the reaction. So instead of just narrowing the time where you calculate the rate, what you can do is to finding the rate after the start of the experiment. Sorry. At the start of the experiment, because as you saw before, the graph is pretty much steep there and looks like a linear expression. That of course depends on the kind of experiment, the course of the experiment, how the data looks like, and so on. So you could actually, for example, try to find a linear mathematical expression which fits with the first data you have collected. Or you could calculate an average rate between time 0, for example. So in this case, you could see an actual way to solve this problem. For example, in the dissolving of chalk experiment, it has been measured that at time 0, the quantity of CO2 was equal to 0 cubic centimeters or milliliters, and after 20 seconds you had a quantity of 50 milliliters. Now that is actually possible so it is actually possible to measure a so-called initial rate, where the initial rate will be the difference of volume created between 0 and 20 seconds, that's 50 cubic centimeters, in 20 seconds time. So the rate of this reaction, the initial rate of this reaction, will be 2.50 cubic centimeters times second at the -1. Now, it would be also possible to measure a so-called rate, an instantaneous rate at a certain point of the experiment. For example, you could choose 2 points here and then calculate the difference of volume here, which I'm marking, for example, divided the time between these 2 points. And you would approximately have a tangent to the plot. But I think the best way of measuring a real reaction rate, it is actually to measure it at a point of time where the linear function actually pretty much resembles the real plot. Of the reaction rate. You can see the blue line is, in this period of time, pretty much coincident with what happens to the change of volume. So that's the best way to fit it. Of course, there are mathematical ways to do that, and when it comes to experiment, if some of you is interested in to find more precise ways to do that, we can do so. This is a rough way, which is good. So this is something you also have to know, which is what we have been speaking about the functions, about the relations between concentration or masses of volume and time, and how this relation is mathematically correctly expressed. That means if you have, and also theoretically, chemically speaking, now if you have, instead of having chalk and hydrochloric acid, if you had a general reaction where reactant A reacts with reactant B, becoming reactant C, product C and product D, you can express the velocity of this reaction by the rate equation, which can be written as follows. How quickly the reaction goes, the rate, is possible to calculate by calculating the differential quotient of how quickly the reactant A disappears, the tangent to the plot made by monitoring the disappearance of or the consumption of the reactant A. And you will have a minus in front of it, because in mathematics something which becomes lesser is expressed by the minus. The reaction rate calculated this way by monitoring the consumption of reactant A is also equal to how quickly the reactant B disappears. So it will also be equal, this differential quotient of concentration of A against time is also equal to the same kind of operation regarding reactant B. So it will be minus the differential quotient of concentration of reactant B against time. But this is also equal to how quickly the product C is formed, which is expressed by a positive differential quotient of the concentration of product C against time, and that would also be equal to how quickly the product D is formed. So it will be equal to a positive differential quotient of the concentration of reactant product D against time. So the tangent to the plot of the consumption of A, or equal to the tangent of the plot of the concentration of B, equal to the tangent of the plotting concentration of C equal to the tangent of the concentration of D. If the case is where you have some stoichiometric coefficients, this could be 1A reacts with 2B, for example, to form two C and 3D, then the way of considering the stoichiometric coefficients in the rate equation, it is that the rate, the velocity of reaction, will be equal to minus 1 divided the coefficient of A times the differential quotient of concentration of A against time. That would also be equal to minus 1 divided, in this case 2, the stoichiometric coefficient to reactant B times the differential quotient of the concentration of B against time. That will also be equal to the stoichiometric coefficient, plus 1 divided the stoichiometric coefficient, there could be 2 here, of the differential quotient of product C against time, will be equal also to the product D, the differential quotient of the formation of D against time, times 1 divided its differential quotient. In this case, it will be 3. That means that how quickly A disappears is exactly how quickly B disappears is exactly how quickly C appears is exactly how quickly D appears. And depending on the stoichiometric factors, you will multiply this expression by 1 divided the stoichiometric coefficients. So, reaction can be reaction velocity, or better, reaction rate, can be measured. That's the first point. If you measure it, you can measure how quickly a reactant is consumed or how quickly a product is formed. If you measure how quickly a reactant disappears, then you will have a non-linear graph, because at the very start it goes quickly with the disappearance, but it gets slower and slower until you don't, for example, have more of the reactant. If you look at the product, then you will see the product be formed quickly at the very start of the reaction, but gradually the velocity of production of product falls until you cannot form any more product. Given the fact that the measuring of velocity is a linear function, you need to calculate a tangent, either at a certain point of the reaction or at the start of the reaction. And it is best to try to find a narrow range of time, because mathematically speaking, in this way you measure a linear function which is a tangent to the real function which describes the reaction. That's why if you express the rate equation mathematically, then you use the so-called differential quotient, which is basically speaking, what we have been saying about narrowing the time where you calculate the rate of the reaction. And if you consider the stoichiometric coefficients, the number before the formulas in the reaction, then it is expressed like this.